So in a string, in a finite automata, the states are changed when certain input is added and a certain condition is cleared, for example, and the transition is done. Then after reaching at some point, if the string accepts, if this string is accepted, it will reach the finite state. So we have to remember these things, that transition will be done only if the set of states are correct. If we give the right state to the input, we give right input to the state and transition happens. So let's go to the next question. So the first of C says difference between NFA and DFA. NFA is non-deterministic finite automata and DFA is deterministic finite automata. So non-deterministic finite automata has more than one transition for each input symbol. As you can see in the diagram on the left side, it may permits the epsilon transition. That is, if we have 1 or 0, then it will go in the right, and it has again the final state. Whereas in deterministic finite automata, there may exist exactly one transition for each input symbol. That is, we have only one input and then one transition according to it. In non-deterministic, it may have many more than one transition for each input depending on the condition. And in the NFA, tables may contain multiple defined entities, where in DFA, tables contain single entities. Now, in the fourth part of first question, we have some true and false questions. So let's see them. First says, if L is the language accepted by NFA-M, then L is also accepted by DFA, which is a correct statement. And because if L is a language which is accepted by non-finite automata machine, then L is also accepted by the finite automata, which is true. Next question says, for every NFA, there exists an equivalent DFA that simulates the behavior of NFA. That is exactly true according to the theory of computations. Next question says, NFA to DFA conversion for n state NFA, there exists at most 2n state in DFA, which is false because it is not dependent on these states. Let's go to the next question. The second question A part says, what are regular languages, and what are the valid operations in the regular RE, that is regular expressions. So the language recognized by finite automata is called regular states or regular languages. It is possible to write regular sets in simple algebraic manner using the following operations called regular expressions, and we have three regular expressions: concatenation, union, and clean star. The B question says, complete the table with correct regular expression table. So we have given the left part of the question, that is regular language, and we have to write the regular expression for each of them. So to understand it, we have a L, language L is equal to 0, 1, 1, 1. That means we have two strings, and we have to write a regular expression for it, which will be 0, 1 plus 1, 0. Again, it says 0, 1, 1, 1 and 1, 0, which will be 0, 1 plus 1, 1 plus 1, 0. Similarly, we are going to write the regular expression for every option given. I suggest you to pause the video and read the table carefully. Let's go to the next part. So as you can see, to understand better, I have given more details about the question. Do pause the video to read each and every line and understand it. If you have any queries, you can message me on LinkedIn. Next question we have, explain Adrian's theorem. So Adrian's theorem says, let P and Q be two regular expressions over sigma. If P does not contain epsilon, then the equation R is equal to Q plus RP has a unique solution given by R is equal to QP clean star. We can also prove this equation using the statements given on your screen. And the next question says, define the grammar for formal languages and complete the following table. So we have to write the grammar for formal languages. A grammar